So this is joint work with Andrew Holroyd and Oded Shram. And Itai Ben-Yamini and Benji Weiss were also involved in the early stages of the discussions. Most of the slides here were made by Ander, who's English, and so that's why they're used in the colors. All right, so this is our last project with Oded. All right, so acute coloring of a graph is a labeling of the graph, labeling of the vertices with the colors 1 through Q, such that adjacent vertices have different colors. Okay, this is a 2 coloring. And the question we're looking at is, can we color all the different vertices so that there's no central authority, and that each vertex is follows an identical algorithm to pick its color? And this sort of question has been looked at in computer science, because if you have an autonomous network of agents that want to communicate with each other, sometimes they have to share parts of the spectrum or share time slices. And in order to do this sharing, they have to pick a coloring on a suitable graph. Okay, so here's one translation invariant coloring on z squared. With probability half, we can pick the coloring on the left, and with probability half, we pick the coloring on the right. So this coloring is translation invariant, but it has long-range correlations. So like if you know the color at a particular vertex, you know the color far away. And in order for the agents to autonomously figure out what color they're going to be, they have to somehow communicate with each other so that they pick compatible choices. Okay, so we're going to be looking at what are known as finitary factors of an IID process. So we're going to let each vertex have its own set of random coins. The 2 at the top there is actually a set membership symbol. Okay, so each vertex looks at a finite set of its neighbors, but it can be an unbounded at an unbounded radius. So as it looks at its neighbors, it decides how much further to keep looking, and at some point it decides to stop, and then determines the color. F is, we say that it's translation equivariant if you can first translate all the randomness of the vertices and then apply the function, or you can apply the function and then translate the coloring, and you get the same answer. Okay, and the distance that you have to look at from a given vertex is known as the coding radius, and this is going to be a random variable. And we're interested in the probability that the coding radius is larger than a certain amount, and the decay behavior of that.
I guess that less than 1 should be less than infinity.
Yes, infinities get turned into 1s.
The 9 gets into a 6.
Yes, right.
Part of the coding. No, it's because he's doing it on a different computer.
Okay, so the 9 doesn't exist, of course. So there is no finitary factor of an IID process, which we're going to abbreviate FFIID, which is a 2 coloring of the integer lattice. So here's a 4 coloring that has exponentially decaying tails. So what we can do is independently color each vertex black or white and look at the clusters that we see here. Now with probability half, site percolation on the square lattice is subcritical, and so the clusters here have exponentially, their sizes have exponentially decaying tails. And so what each cluster can do is, each vertex can do is it can explore its cluster. It doesn't have to explore very far, and it can take some canonical vertex of the cluster, say taking the leftmost vertex of the bottom row, and that becomes somehow the identity of the cluster. So that particular vertex can then pick a random 2 coloring. And so the black clusters are going to color themselves randomly red or blue, and the white clusters are going to color themselves randomly green or yellow. Like so. And so this is going to be a proper 4 coloring because vertices within the same cluster are 2 colored, and if you're going across clusters, you're using different sets of colors. Okay, so the Sadia is greater than or equal to. For any d greater than or equal to 2, there's a finitary factor of an IED process, which is a 3 coloring that has power law correlations, and we can show that in fact any FFIID 3 coloring has to have power law correlations. And furthermore, there's a 4 coloring that has tower law correlations. So the probability that the coding radius is bigger than r is less than 1 over a tower function of r. And any FFIID Q coloring has to have tower law behavior. This lower bound is due to nonlineal. And the constants that you see here depend on the dimension and the number of colors. For dimension 1, the picture is almost the same, with the exception that instead of power law correlations for 3 colorings, you can do it with tower law behavior. And this is also essentially due to lineal, the 3 coloring. Okay, so I'm going to show a 3 coloring of z squared with the power law tails. What we can do is in each box randomly draw the left to right diagonal or the opposite diagonal with probability half. This gives bond percolation on the Euclidean lattice if you rotate 45 degrees. So this is bond percolation on the green sites, and the purple bonds are the dual clusters. Okay, so using facts about percolation, each cluster is going to be finite, and the probability that a cluster is beyond a given size is going to have power law behavior. Okay, so we're going to color the clusters as follows. Think of this as the tree of clusters. So each cluster is surrounded by some other cluster, and so that cluster is above it in the tree. There's a unique cluster, which is the innermost cluster surrounding it. That's the parent. And this is the tree of all the clusters. And if each cluster flips a coin with probability half, it comes out red. And we're going to say that each cluster furthermore looks at its parent. And if the parent is also red, then it colors itself white. And so all the red vertices, all the red clusters that you see here, are non-adjacent to one another. And to color the other clusters, we can just pick a 2 coloring. Okay, and so the distance that you have to look up in the tree is, well, in the tree distance it has exponentially decaying tails, but in the original Euclidean lattice, it's going to have power law tails that you have to look out to determine the nearest ancestor that's red, and therefore what color that the given cluster is going to be. Okay, so why you can't do better in power law behavior? This is essentially related to the fact that for 3 colorings there's a height function. The 3 colorings are shown here. We're going to identify the colors with the numbers 0, 1, and 2. And these numbers can be lifted to heights so that the height modulo 3 gives the original number. And the reason that this works is that if you look at any square, well, you can check that going around the square. So here we're going up, up, then we have to go down, and then down, and there are only finitely many possibilities to check, and they're all consistent. So going around the square, the heights stay the same. Okay, so anyway, this is a well-known height function. And we're going to show that if you have any FFIID 3 coloring, that the variance in the heights is going to have to be bounded if you have better than power law correlations. And this is going to ultimately lead to a contradiction. Okay, so we're going to let h of z prime be the height difference between 2 vertices z and z prime. And because these height functions in general can have a tilt, we're going to let h tilde be the height difference minus the expected height difference. And we're going to let rho of r be the worst case over pairs of vertices in the lattice of the expected modified height correlations between them, where the pair of vertices have to have distance at least r, and z naught prime are distance 1 from each other, and likewise for z1 and z1 prime. And the claim is that the sum here of r times rho of r goes to infinity. And of course, if we have better than power law correlations, it's not going to go to infinity. Okay, and so the way we can do this is by looking at h tilde between some vertex v naught and some other vertex vn, which is far away, say on the horizontal axis. And because h tilde has been set to have expectation 0, the variance of h tilde from v naught to vn is just the expected h tilde squared. Now, this height difference can be represented in 2 different ways. This can be represented as the sum of height differences along the straight line at the bottom, or along the path going on the top. And this is essentially where we're using the fact that we have more than one dimension. And to evaluate this expected square, we can use the first representation and also the second representation and multiply them together. And add up all the correlations here. Because most parts of the path are far from one another, it's not too hard to check that this expectation is bounded by the sum of r times rho of r, where r goes from 1 to some constant times n. And in particular, that's bounded. Okay, so I'm not going to go through the details of deriving a contradiction from that, but the proof follows from that. Okay, so here's how you can make tower coloring on Z. Okay, so
Could you still say something about what's the problem with bounded variance? Not the details, but the philosophy.
the philosophy. Well, okay. Well, okay. So basically, the problem is that if you look at H mod 2 at the origin, it's going to have the same value as H mod 2 at some vertex distance 2n away. And if you have bounded variance, then somehow intuitively there's like a smallest value that it's likely to take. And if it's going to take that smallest value in the height difference from 0 to 1 compared to 2n to 2n plus 1, it's going to have to pick, they're going to see the same most likely smallest value. And when you look at it from vertex 2n plus 1 to 2n plus 2, you're going to have a different most likely smallest value. And so somehow there's this two-coloring thing that comes up again. So at an intuitive level, that's what's going on. Okay, so this, looking at colorings on Z, essentially came from the computer science world, where instead of looking at the full integer lattice, they're more interested in a finite graph, say the ring, and they want to generate a random coloring rapidly. And so the tower law tail behavior translates to log star n number of rounds for a distributed algorithm to find the coloring. And so the strategy here is if you have each vertex has a unique label, say by picking a random number from 1 to n squared. So these are the bits of that number. So most likely neighboring vertices are going to have different numbers. And what you can do is write down the index of the first bit where the bit values are different, and also write down which side has the 1 compared to the 0. And this gives a different set of labels for the vertices. Now, you can't, assuming you have a proper coloring up originally, you're not going to get adjacent labels equal over here. And the reason is like, for example, if you had bit position I, where the left vertex had a 1 and the right had a 0, next to it, you're not going to have the same pattern because then the left vertex would have had a 0. Okay, so this essentially gives a new coloring with twice log of the original number of coloring colors. And if you repeat this log star n times, you're going to get down to a constant number. And to do this on Z, you need to do a little bit of patching to fix things up because you're going to have some color clashes to begin with. And so this would give a 6 coloring of Z, which you can then convert into 3 coloring of Z by this process of color elimination shown here. So what's shown here is that we take the largest color, 6, and all the 6s get recolored by the smallest color that's legal. And then repeat that with 5s and then the 4s. And then that will give 3 coloring. Okay, so something related works for general graphs with degree-bound delta. And I'm just going to quickly indicate how this is done. It makes use of a result due to Erdős, Frankel, and Firetti. And what they showed is that you can have a family of sets of the elements 1 through k, so that no set is covered by d other sets. And also where the number of sets in the family is exponentially large in k.
No set is covered by the union of the others?
Right, not covered by the union of the others. And a probabilistic construction works here. For each set, you pick each element randomly with probability 1 over d plus 1. There are going to be many elements of any given set, and for each of those, there's a good chance that it's not in the other sets, and so the probability that it's covered is exponentially small. Okay, so if you have a proper n coloring, gamma, you can turn it into a proper k coloring, gamma prime, according to this color reduction formula. So gamma prime at a vertex becomes the smallest element of S of gamma of V, excluding the S of gamma of W's, where W ranges over the neighbors of the vertex V. Okay, because none of these S's is covered, this is a well-defined function. And because the new gamma prime of V is an S of gamma V, and the neighboring vertices are an S of gamma W, and they're excluded here, we're still going to get a proper coloring. So the first idea would be to pick a large n so that every node is likely to have a distinct color from its neighbors if you color it from 1 to n, and then do this color reduction log star n times. Okay, so if you have an infinite graph, of course, there are going to be some exceptions, and what you can do there is iterate this many times for large values of n1, n2, and so on, where we can do these color reductions from n sub I plus 1 down to n sub I. And if we pick an n sub I coloring, we can reduce it down to an n sub 1 coloring, where the colors are delta plus 1 up to delta plus n sub 1. And in the event of a clash, when you take this minimum, that's the minimum of an empty set, and so that's represented by the symbol infinity. Okay, so after you do the color reduction, you can do the color elimination, which was described earlier. Convert those to the colors 0 through delta, and then those colors are fixed. And the color infinity just needs to be done in a later round. Okay, so for example, for z squared, this shows that there would be a 5 coloring. That's an FFIID process with Tower law correlations. Okay, so I'm going to describe a coloring strategy for the triangular lattice. So the three colorings are rigid. So if you have any triangle, if you color the three vertices of that triangle, that determines the colors everywhere else in the lattice. Okay, but if you have four colors, it's not rigid. And so we can hope to have an FFIID for coloring. And what we have here is a graph of all the different three colorings. So there are 4 factorial ways to three color the lattice using 3 of the 4 colors. Okay, so here instead of red, green, and blue at the bottom, that's denoted as 1, 2, and 3. And all right, I mean, this just tells you what numbers to substitute for red, green, and blue. And there's a natural adjacency structure on these 3 colorings. If you change one color of the 3 coloring to the other color that's not in it, for example, 142 can be changed to 342. Okay, so every 3 coloring is, in a sense, adjacent to 3 other 3 colorings, and this is the graph of 3 colorings. It's connected, and it has diameter, which is at most 4. And so the idea is that we're going to locally 3 color things and stitch them together. Okay, so the way we do this is we use site percolation on the triangular lattice. We're going to think of the sites of the lattice colored blue and yellow, and we're going to look at the clusters that we see. We have blue clusters and yellow clusters, and they're nested within one another. And we can look at the tree structure of these clusters. And the idea is that each cluster is going to propose a coloring for all of its descendants. And there's going to be some coin flips to determine whether or not the proposals are successful. Okay, so this is the tree of clusters. So each cluster is going to flip a coin. If it comes up heads, that's shown as a red circle. And if it came up heads and each of its 3 closest ancestors also came up tails, then that's shown as a red disk. And if a cluster has a red disk, then it proposes a coloring 3 coloring for its descendants. Okay, and of course these colorings have to be compatible. And so the way we do this is that, so like this cluster proposes one coloring, this cluster proposes another coloring. The coloring that this cluster actually gets is the coloring that this cluster proposed. And since this cluster also wants to color its descendants in some fashion, what we do is refer to this graph here. We have these 2 different colorings, and there's going to be some path of distance at most 4 between them. So each of these descendants is going to be colored according to a coloring which is 1 closer to this cluster's proposed coloring than it was to that cluster's proposed coloring. And because these red disks are of distance at least 4 from one another, every cluster is going to be assigned some 3 coloring, and adjacent clusters are going to be assigned 3 colorings that are adjacent in that original graph, which means that there are going to be no color clashes between them. Okay, and with 4 colorings of the triangular lattice, In fact, power law correlations is the best you can do. And the reason for that is that there's a height function associated with them. What you can do is group the colors into two groups of two, say red and green and blue and yellow. And around any triangle, there's going to be exactly one edge for which both endpoints of the edge are colored within the same group. And for that edge, we can just delete it. And we get a lozenge tiling. And lozenge tilings are well known to have height functions. You can see one here. And so then the same height function argument that we saw earlier applies to four colorings for the triangular lattice. Okay, so for z squared, we saw that there's a 5 coloring with tower law tails. So in fact, there's actually a 4 coloring with tower law tails. And I'm not going to go through it, but the basic idea is that you make these 2 labelings by these blocks so that each of these blocks has bounded size, and like no 2 yellow blocks are going to touch each other. And then each of these blocks can be colored independently with 2 colors. Okay, so in addition to colorings, there are all kinds of other structures that one can think about making. So more generally, a shift of finite type is going to be a configuration which satisfies certain constraints. If you look at any block, it's going to be, all right, the 1/2 there is, yes. And if you look at blocks, they lie within some set of valid configurations. So for example, for colorings, the valid configurations are that adjacent vertices have to have different colors. Okay, so in one dimension, if we want to pick a random shift of finite type, then we have 3 possibilities. Either there's no process that has decay of correlations or trivial tails, and that was, for example, the 2 coloring. Or there's a finitary factor of an IAD process, which is a valid configuration that has power law correlations, and there's no FFIID that has better than power law correlations. Or the third possibility is that all right, well, all right. The fourth possibility is that you have tower law tails. I'm sorry, that's the second possibility. The third possibility is that you essentially have 0 coding radius, so that all configurations are allowed. So in 2 and more dimensions, we see each of these behaviors. Either there's no way to generate the process, you have power law tails, you have tower law tails, or you have 0 coding radius. And we don't know if there are any other shifts of finite type that have any other intermediate behavior, like if there's some configuration for which there's an exponential law FFIID and you can't do tower law, for example. Okay, so there are some related concepts. So a finite factor, which has fixed bounded coding radius, is called a block factor. And so we know from the results that I talked about earlier that there are no block factor colorings. And a process is called k-dependent if the values that you see to the left of 0 are independent of the values that you see to the right of k minus 1, or from k onwards. So it's obvious that a block factor is going to be k minus 1 dependent, and it's less clear that you have k minus 1 dependent things that aren't block factors, but this was shown by Arison, Gilot, Keen, and de Volk. And so one natural question is whether or not there's a k-dependent Q coloring on Z. And
There's another symbol there, yeah, but it's not. That's a P block factor, not Q.
right.
No, Q minus 1 dependent and it's not a P block factor.
Right. Okay, so we can show that there's no one-dependent 3 coloring, but we don't know anything about any other values of k and q.
What dimension was the question?
This is in dimension 1. Okay, so I'm going to stop here.
Any comments or questions? Ron?
I didn't understand your argument for the variance showing that the height function has to have a non-bounded variance of time. Would it apply, or a similar one would apply, if it has a uniform coloring, which you a priori don't know if it is an FFIID or not? If you take uniform coloring out of all possibilities, then would the height function of that necessarily have a non-unbounded variance going to infinity height?
Okay, so
Uniform among all classical colors.
yeah, so you can pick a uniform coloring, and you can ask whether or not you can construct that as an FFIID process. So that's not exactly the question that we looked at. So we were looking at how can you make a coloring which is an FFIID process.
I understand, but does your argument apply to say anything that the height function of that is not as variance to infinity? The argument is sketched between H and H2. Oh, that has to be there.
Pretty much.
I had one question. Have you looked if you can make these mappings so it's invertible rather than using uniform, using a finite?
No, so we didn't do that. Yes, so you're asking about whether you have like a finite number of values or something like this?
On top, and whether you can make this mapping invertible.
No, so we assume that each vertex has an infinite supply of randomness.
Right. Any other